Oh, oh, okay. I want to go over the practice final number 3 with you. The rest of the questions, we've already done the multiple choice in class. So in this problem, the first question is what's the domain? Well, we just want to look at this function and ask if there are any x's we can't put in. And you couldn't put in x equals 0 because that would make the denominator 0. So this is negative infinity to 0. That's a union symbol. You can make it a comma. 0 to infinity. All real numbers except 0 are in your domain. All right. The original function also tells you about vertical and horizontal asymptotes, which is question E on the page. Let's go ahead and handle those. When that denominator is 0, the numerator would not be 0. Non-zero over 0 is a vertical asymptote. So x equals 0 is a vertical asymptote. If we take the limit to infinity, since this is a polynomial, we only have to take it in one direction. For other functions like logarithmic or exponential, you have to look both ways on the limits to positive infinity and negative infinity. But this time, it's enough just to look one direction. We're going to use the fact that the degrees, 2, are equal in the numerator and denominator. That means we can use the leading coefficients, 1 over 1, to get our limit. And if the limit is 1, that means that your horizontal asymptote is y equals 1. So the two asymptotes are shown here, and that answer is part E on this page. All right, the first derivative is going to tell us about intervals of increase, decrease, and relative maxes and mins. Our first derivative is not defined at 0, but we knew it wouldn't be because that's its vertical asymptote. So we want to go ahead and take the, excuse me, I had a control box in my way there, sorry. Okay, so for the first derivative, we're going to take this 4x, we know that it's not defined at x equals 0, and we're going to take and set 4x minus 20 equals 0. You see that right there, and that gives you x equals 5. Now if you simply make a sign chart, and they started one over here, so I filled in at 0, we had a vertical asymptote, at 5 we had a 0. We can just plug a number into each of these three ranges, and we'll find out by plugging in, say, a 10, that this fraction is positive. So I've got a positive sign there. Plug in a 1, you'll see that that fraction becomes negative. Plug a negative sign in there. By plugging in a number in this range, like negative 10, you'll find that that fraction is a positive number again. 10 would have been, negative 10 would have been negative, a negative over a negative would have made that positive. All right. That tells us then that where we have the plus signs, our function is increasing. That would be negative infinity to 0 and also 5 to infinity. Where we have the minus sign here, our function is decreasing. So our answer is negative infinity to 0, 0, and 5 to infinity, where it's increasing. We can also answer from that part, from our sign chart, part D of this question. D asks us for extrema. That means maxes or mins, and they want us to identify the type. We look for sign changes in the first derivative. We do not look where the sign changes on an asymptote, so that one doesn't count. But here, the first derivative changes from negative to positive at x equals 5. And so that's decreasing to increasing. That's a minimum. And what we want to say is we have a local minimum at x equals 5 because f prime changes from negative to positive at 5. Okay, what's left for us here is the concavity question. Concavity is based upon the second derivative. Second derivative is shown up here. It's also written down here, so I'll just point to it in the lower section. It's that 60 minus, sorry, It's that 60 minus 8x over x to the fourth. Well, this is a nice one to work with because, for one thing, the denominator is always going to be positive. Okay, so we need to know when is it undefined or when is it 0. It's undefined, it doesn't exist when x equals 0, but that was our vertical asymptote, so that's what you see over here. Now, 60 minus 8x equals 0, and a fraction 0 only when its numerator is. When if you solve that, you get 8x equals 60, x is 60 over 8. Divide that by 4, you get 15. Divide that by 4, you get 2. 15 halves is your answer. And I changed that number. I'm not sure what that was they had written there. But at x equals 15 halves, the second derivative is 0. So we need to get pluses and minuses again and again. Since the denominator is always positive, you're really only plugging in here. So if you plug any number out here like bigger than 15 halves, which is 7.5, plug in 10, you get 60 minus 80, that's negative. Plug in a 1 in this region, you get 60 minus 8, that's positive. Plug in a negative 1, you get 60 minus a negative, this becomes negative 8, and 60 minus a negative 8 is 68, that's positive. So we know that we are concave up, where we see the plus signs, that is negative infinity to 0 and 0 to 15 halves. Again, that could be a comma, and you do want to split them into two intervals whenever you're on each side of an asymptote. I think that answers all the questions on that page. Your next problem, you have a downward parabola, 8 minus x squared. You noted that it crosses the y-axis, by the way, when x is 0, so 0, 8's on that guy. And you have an upward parabola. This one crosses the y-axis down here at negative 10 if you put a 0 in there. So you know that the downward parabola is on top, the upward parabola is on the bottom, and they enclose this region. You need to find the intersection points, and you find the intersection points of those two graphs by setting these equations equal. I've shown that work over here, and it works out pretty nicely. You get x equals plus or minus 3. So when we're doing the area enclosed by curves, we integrate between our limits of integration, which will be our intersection points, the top function, which is the downward parabola, minus the bottom function, which is the upward parabola. And so that is the integral they performed here. The integral from negative 3 to 3, that's the downward parabola minus the upward parabola. Hopefully that's what I said before. Downward parabola was on top, upward parabola was on the bottom. So it's the downward parabola, upper function, top function minus the lower function, the upward parabola. Okay, so downward minus upward. Well, you want to simplify that before you do anything else, though. So they've simplified it over here, making the integration much easier. They've shown down below the antiderivative. This would be 18x, and then here you'd add 1 to the power, divide by the new power, and have 2x cubed over 3. So that's what they've got. At that point, it's just plugging the 3 in to these two, and then minus plugging the negative 3 in to those two. It's always the upper limit plugged in minus the lower limit plugged in. That's their work here, and the answer is 72. Okay, here comes a max-min problem. This time it is a box, and we have 24 square inches of material. You should interpret material as being surface area, and you've got the equation then that your surface area is 24. We'll have to talk in a second about how they generated that. We're supposed to find the largest possible volume. So our answer is going to be a volume. We are maximizing volume. Okay, to start off with, you need a picture. Okay, so here's the picture of a box. It has no top. That's open up top. It has a square front. So I sort of marked on this already. That was X. That would be X. You know, this all around this front is all X's. All around the back is all X's. Square front. We don't know how long it is and it has a square back. We need a different variable there because we don't know how long that is supposed to be. Okay, so at that point, you can get your surface area. You got a front and a back. They'd be x by x. That would be 2x squared for them. And then the other three sides, remember, open top, are all x by y. So that would be 2x squared plus 3xy equals 24. That's called our constraint or secondary equation here. We're maximizing volume. The volume is length times width times height, which would be x squared y. Okay. I don't know what down here where they call that Q. I think I would call it V for volume, but it's not my solution here. Okay. So we always are going to take our constraint equation, the thing that is a number. We know surface area is 24. We can't change that. So we're going to take that and solve it for the variable, in this case, solve it for y, so I can stick it right there. When we have solved that for y, here's the expression we get. So this is the same Q, they called it, and we've got this expression in the place of y. Again, before you do the derivative, simplify. It simplifies to this expression. What you want to do always on these problems when you're finding maxes and mins, because you're looking for sign changes in the first derivative, is take the first derivative and set it equal to 0. Here's that work. You end up, solves out nicely. X is 2. I went and found the y value, at least I think I did over here, using the equation 24 minus 2x squared over 3x. That's 24 minus 2 times 2 squared. 2 squared is 4. That would make that an 8. 24 minus 8 is 16. And we're dividing that by 3 times x. 3 times x would be 3 times my 2 that I found over here. And so that would make that 3 times 2 is 6. 16 over 6, 8/3. That's a valid box. I was just checking, did we have a good box here? Good length and height, and we did. Okay. In that event, the last thing to do, well, two things to do. One, we have to verify that we have to get our volume by taking our 2 that we found and sticking it there. And we get 32 over 3. I guess I could have taken my 8/3 over there. And, that's interesting. Oh, I'm sorry. It's 2 squared, so that makes sense. It's a 4. Okay, so 2 squared, 4 times that number, which is our y. All right, 32 over 3 is the correct volume. All righty, so we need to justify that that's in fact a maximum. Here's the justification I like the most. This second derivative is easy to take. It's negative 4x, and for any positive x value, which is the only ones that make sense in our problem, this is negative, and that means that our only critical number is going to be a maximum. The function must be, you know, rising and then falling, and there's that. Okay, they justified it in a variety of ways. One that, sort of unusual is they made it a closed interval problem. They said, the smallest x I could possibly have up here is 0, which means that really I got no box, but it's a boundary. The largest would be when I could have no y, and if I have no y, then I get the square root of 12. So they said down here that when the endpoints were x equals 0 or x equals root 12, you'd have no volume, because essentially you have no box. And so the only critical number we found is bigger than that. It must be the maximum. That's what they're saying in this point 1. I'm not crazy about that explanation, but because I don't really have a box at the ends, but it is correct. At least I think it is. Okay. I kind of like mine. Here's another one. They could do a sign chart. You don't have to do the chart, but they could make the argument that the derivative of q, q prime, is positive up to 2, because there you like put a 1 in there, it's positive, and negative to the right. And they had their signs mixed, so they had their sign mix right here, so I changed that. And that would give you a maximum as well. And then here's a second derivative argument, sort of like mine, except they just checked out the second derivative at the single point x equals 2. All right, here's our related rates problem. Pretty typical one. I reinforced these. These are really light. I hope you can see them. I hope you're looking at your own paper. I reinforced this one. We've got Alice going north and Bob going west. At some point, they're starting off at the same point as tree. When Alice is 30 feet away from the tree, she's moving 20 feet per second. That gives me, I wrote down here, dx dt is 20. Bob's going over this way. When he's 40 feet away from the tree, at that instant, he is going 10 feet per second. So the y at that instant is changing at 10. So dy dt is 10. And they're asking at that instant right there, how fast is the distance between them changing? So these are all changing quantities. Okay, I did go work out that at that instant, the third guy, which is this z, which is what we're trying to find, is dz dt, that by the Pythagorean theorem, z would be 50 at that point in time. But these are three changing quantities. We don't want to plug their values in until after we've taken the derivatives. So what relates them all? It's the Pythagorean theorem. It's sort of light there, but it's x squared plus y squared equals z squared. Take the derivative all the way across. You get this. You're differentiating with respect to t, so 2x times dx dt plus 2y times dy dt is equal to 2z times dz dt. Okay, at that point you plug in all the numbers from the problem. We knew that x was 30 because that's how far Alice was away. That was the Alice direction there. That she was going at 20. Okay, dx dt was 20. That y was 40, and he was moving at that point in time at a rate of 10 feet per second. So there's a 10 here. And then that equals 2z times dz, times dz dt, and they filled in 50 right there, 2 times 50 times dz dt. At that point, you're only solving this with all numbers in there. There's your only thing you're solving for. You're solving for dz dt, and the answer becomes dz dt is 20. So it says the distance between them is increasing at 20 feet per second. And again, this is very light, but hopefully you're reading these solutions off of the solutions that are on Prism. Our final problem, the only thing that we know that looks like this is the limit of a sum is a Riemann integral. Inside here is a Riemann sum. When you're just adding them up, putting the limit makes it an integral. So you have to figure out what's the function that we're integrating, and pretty clearly it's the sine function. We need to figure out what our delta x is. I mean, how wide are our rectangles? And they snuck that guy and put him right at the start. Remember, delta x would be b minus a over n. So that expression, that's how wide each rectangle is, and we're multiplying the width, delta x, times the height. Okay, so that's a little bit of a help in the problem. And we can see that, you know, if we're not using I equals 0, which would be like the left endpoint, we're using I equals 1 as our first, but if I were 0, this would just be pi over 4. That's our lower limit of integration. when I equals n, the last value, let's look at this version down here. Here you can clearly, I guess, see better. When I equals 0, all I did was distribute this. When I equals 0, that would leave you with pi over 4, and why I equals its last value, make that an n, you get n over n, they cancel, and you've got pi over 4 plus pi for your last value, and that's 5 pi over 4. So we're integrating from pi over 4 to 5 pi over 4 sine x dx. We would know that the integral, we've identified it, the integral of sine x is negative cos x, and they're saying that they're evaluating it at 5 pi over 4 and negative, and also pi over 4. So we get this, and then we just evaluate with our knowledge of the unit circle, and eventually we get down there. Hope that helps.